Scene script. Ever wondered how ships navigate through foggy nights or how aircraft avoid mid-air collisions? The answer lies in radar technology. Radar, an acronym that stands for radio detection and ranging, is a technology that you may not see, but it's always there, quietly guiding and protecting. From the vast expanse of the ocean to the limitless skies, radar technology keeps a watchful eye, ensuring safe and smooth voyages. Imagine you're a ship captain on a foggy night. The visibility is practically zero, and you're sailing blind. But thanks to radar technology, you can navigate through the thickest fog, avoiding other vessels and obstacles, and safely reach your destination. Now let's shift our gaze upwards to the skies. Air traffic is a complex and highly coordinated ballet. Each aircraft, whether it's a small private plane or a massive commercial jet, needs to maintain a safe distance from others. This is where radar technology comes into play, providing real-time data to air traffic controllers, helping to prevent mid-air collisions and ensuring the safety of millions of passengers each day. But the applications of radar technology don't stop there. From meteorology, where radar helps predict weather patterns, to space exploration, where it's used to map the surfaces of other planets, radar technology has proven to be indispensable. As we move forward into the 21st century, the importance and applications of radar technology are only growing. With advances in technology, radar is becoming more precise, more reliable, and more integrated into our everyday lives. It's not just about avoiding collisions anymore. It's about understanding our world and the space beyond in a way we never thought possible. And the fascinating part, radar technology has been evolving since its inception in the early 20th century, and it continues to do so, constantly adapting to our changing needs and technological advancements. So, ready to unveil the mystery behind this invisible guiding force? Let's dive in. Radar, an acronym for radio detection and ranging, has a simple yet fascinating mechanism. So let's dive right into the basics of radar. At its core, radar is a technology that uses radio waves to pinpoint the location, speed, and direction of objects. It does this by emitting a radio wave and then waiting for the wave to bounce back after hitting an object. The time it takes for the wave to return gives us the distance of the object, and the shift in the wave's frequency tells us its speed. It's a bit like shouting in a canyon and waiting for the echo to come back, except with radio waves instead of sound. Now there are two main types of radar systems, primary and secondary. The primary radar system works just as we described, by emitting a radio wave and waiting for it to bounce back. It's simple, effective, and can detect almost anything in its path, but it lacks detailed information. On the other hand, we have the secondary radar system. This system is a bit more complex. Instead of waiting for a simple echo, the secondary radar sends out a signal that requires a response from a transponder, a device that can be found on most aircraft today. The transponder receives the signal, encodes some information onto it, like the aircraft's identity and altitude, and sends it back to the radar. This gives the secondary radar system a wealth of information that the primary system just can't match. But it's not all sunshine and roses with the secondary system. It relies on the aircraft or object having a working transponder, which isn't always the case. This is why most radar systems today use a combination of both primary and secondary systems to get the best of both worlds. Now that we know the basics, we should look deeper into how these radio waves work in a radar system. But that's a topic for our next scene, where we'll delve into the fascinating world of radio wave propagation and radar signal processing. Stay tuned. The working of radar technology might seem complex, but it's all about sending, receiving, and interpreting signals. Let's break it down into 3 steps: transmission, reflection, and reception. First, the transmission. A radar system begins its process by emitting a radio signal into the atmosphere. This signal is in the form of a high-frequency electromagnetic wave. The radar's transmitter generates this wave, which is then amplified and directed into a beam by the antenna. This beam travels at the speed of light, piercing through the air in search of an object. Now, on to the second step, reflection. When the radar's radio wave encounters an object, be it a plane, a ship, or even a storm cloud, it bounces back. This is because the electromagnetic wave has hit a surface that reflects radio waves. Imagine throwing a ball against a wall. The ball comes back to you, right? It's the same principle here. The radio wave hits the object and then bounces back towards the radar system. The nature of this reflection can tell us a lot about the object. Its size, shape, and even what it's made of can be inferred from the way the radio wave is reflected. Finally, the third step, reception. The radar antenna, which doubles as a receiver, picks up the reflected radio wave. This returning signal is often referred to as an echo. The time it takes for the echo to return gives us the distance of the object from the radar system. It's simple physics. The speed of light multiplied by the time it takes for the echo to return, divided by 2, gives us the distance. This is because the radio wave has made a round trip, out to the object and back again. But what about the direction of the object? That's where the radar antenna's orientation comes in. By knowing which way the antenna was pointing when it received the echo, we can determine the direction of the object, and there you have it, the working of radar technology. A continuous cycle of transmission, reflection, and reception. The radar system is always listening, always waiting for the echo of its own signal. It's a dance of electromagnetic waves, bouncing back and forth, painting a picture of the world that we can't see with our own eyes. So that's how a radar system detects objects. But what happens after detection? That's where the processing of radar signals comes in. Once the radar receives the reflected signals, it's time to make sense of them. In the heart of every radar system, there's a complex process of signal interpretation that happens almost instantaneously. When the radar's receiver picks up the reflected signals, the first step is to amplify them. This is crucial because the signals often return weak and diluted, having traveled great distances or through challenging conditions. Next, the radar uses a process called pulse compression. This is where the radar compresses the long-duration signals into short, sharp pulses. It's like taking a long, drawn-out echo and squishing it down into a brief, clear ping. This helps the radar to accurately calculate the distance to the object by measuring the time it takes for the signal to return. But what about determining an object's speed, you ask? That's where the Doppler effect comes into play. The Doppler effect is a fascinating phenomenon, where the frequency of a wave changes based on the observer's perspective. It's the same reason an ambulance siren sounds different as it approaches you, and then drives away. In the context of radar technology, the Doppler effect is used to measure the velocity of moving objects. If an object is moving towards the radar, the frequency of the return signal will be higher than the original. Conversely, if an object is moving away, the frequency will be lower. By comparing the original and return signal frequencies, the radar can calculate the object's speed. But it's not just about location, distance, and speed. Modern radars can interpret the shape and size of an object too. They do this by analyzing the signature of the return signals. Different objects reflect signals in unique ways, creating distinct signatures that radars can recognize. And just like that, within a matter of microseconds, the radar has processed and interpreted the signals. It's identified the object's location, calculated its distance and speed, and even determined its shape and size. And voila! That's how radar technology helps in detecting and tracking objects. Radar technology has come a long way since its inception, and its future is even more promising. It's not just about detecting objects anymore. Today, radar is a versatile tool, revolutionizing fields as diverse as meteorology, astronomy, and autonomous driving. It's helping meteorologists predict weather patterns with incredible accuracy, aiding astronomers in mapping distant galaxies, and enabling self-driving cars to navigate safely and efficiently. But that's not all. The potential of radar technology is virtually limitless. Imagine a world where drones use radar to deliver goods right to your doorstep, or rescue teams employ it to locate survivors in disaster-stricken areas. Radar is poised to play an even more critical role in ensuring safety and efficiency across various sectors. So next time you marvel at a plane soaring high or a ship sailing smoothly, remember the unseen power of radar technology that's guiding them.